Physics 30s, once again, here I am, Mr. Thompson. All right, page 80 of the workbook, we're looking at Snell's law. So this becomes a little bit technical here and a little complex, so just hang in there, everyone. N1 sine theta 1 equals N2 sine theta 2. So what we have here is we have a light ray that is moving from one medium through the interface into another medium. Do you notice the fact that theta 1 here is smaller than theta 2, so it's refracting away from the normal. That means it's going from a more dense medium to a less dense medium in this example. In general, though, we can actually relate that to this ratio of the speeds in the media and the ratio of the wavelengths. Now, if you check out the formula, what's kind of nice is that they use ones and twos, which is fine. In the context of a problem, I might change it to, W, so theta W for an angle in water, be it an angle of incidence or an angle of refraction. So I try and use subscripts to indicate what I'm doing in the question. But what's nice to realize here is that the ones line up all the way across except for the indices of refraction. See, we've got N2 over N1. All the other ones go 1 and 2, 1 and 2, 1 and 2. And so it's easy to use that to kind of set up quick equations. So what we typically have here is one equation, and we know three of the four, so we can solve for the unknown. Okay, so we can relate the angles to the indices of refraction, to the ratio of the speeds, or to the ratio of the wavelengths, and of course mix and match. So ratio of the wavelengths to the indices of refraction. All right, so there's a lot of practice we can do here. Let's look also at the fact that the frequency does not change between the media. The speed and wavelength do, but the frequency depends on the source, so it remains constant as the light ray moves from one medium to another. All right, looking at total internal reflection. So recall, when light travels from a slow to a fast medium, so high N to low N, like above here, there are two rays, a reflected ray, where the law of reflection happens, and a refracted ray, which bends away from the normal. So the refracted angle is larger than the incident angle. What happens when the angle of incidence is increased? We end up getting to the point where we have a critical angle. If we increase the angle of incidence enough, eventually the angle of refraction is 90 degrees. Now, theta r equal to 90 degrees, really that's the incident angle. It's called a critical angle. Okay? So the incident angle is at some value, called the critical angle, to make a refracted angle of 90 degrees. Total internal reflection. So if the angle of incidence is greater than the critical angle, then there is no refracted ray, and there's only reflection. So here's the case where you have, right, some of the wave is reflected, and some passes into the other medium. Okay, the lower optical density medium. Here, of course, is showing that critical angle. And then if it's moved just a little further than that, okay, so in other words, making a larger incident angle, then internal reflection occurs, and we call it TIR. It says, note, TIR cannot occur when the ray goes from a fast medium to a slow medium. Why? Well, the ray bends towards the normal. So even if the incident angle is 89 degrees, the refracted angle will still exist. All right, I'll do a few problems coming up here. We're going to start on page 81 just after a quick little break.